Natural numbers. Natural numbers are the most basic numbers used for counting. They start from 1 and continue indefinitely, like 1, 2, 3, and so on. The set of natural numbers is represented by the letter n. The natural number set is defined as follows. Examples: 35, 59, 110. Addition and multiplication of natural numbers are closed, associative, and commutative. The identity element of a natural number under addition is 0, and under multiplication is 1. Whole numbers. Whole numbers are also known as natural numbers, with 0 included. The set consists of non-negative integers, where it does not contain any decimal or fractional part. The whole number set is represented by the letter W. The whole number set is defined as follows. Examples: 67, 0, 49, 52. Whole numbers are closed, under addition and multiplication. 0 is the additive identity element of the whole numbers, and 1 is the multiplicative identity element. Integers. Integers are defined as the set of all whole numbers, with a negative set of natural numbers. These numbers can be positive, negative, or 0, and they extend infinitely in both directions on the number line. The integer set is represented by the symbol z. The set of integers is defined as follows. Examples: 52, 0, 1, 16, 82. Integers are closed under addition, subtraction, and multiplication. The commutative property is satisfied for addition and multiplication of integers. They obey the associative and distributive properties of addition and multiplication. The additive identity of integers is 0. The multiplicative identity of integers is 1. Rational numbers are numbers that can be written as fractions in the form of p over q, where both the numerator, p, and the denominator, q, are integers. The only rule is that the denominator cannot be 0. These numbers can also be whole numbers or decimals, as long as the decimals are either repeating or terminating. A rational number is represented by the letter q. Examples: 7 over 2, 10 over 2. Rational numbers are closed under addition, subtraction, multiplication, and division. They satisfy commutative and associative properties under addition and multiplication. They obey the distributive property for addition and subtraction. Rational numbers are numbers that cannot be expressed in the form of fractions, or p over q. Their decimal expansions are non-terminating and non-repeating. They are used in geometry and advanced mathematics. They are represented by the letter p. Examples: the square root of 2, pi, Euler's number. Irrational numbers are distributive under addition and subtraction, and satisfy commutative and associative properties under addition and multiplication. Real numbers include any number, such as positive integers, negative integers, fractional numbers, or decimal numbers without imaginary numbers. They are represented by the letter r. Examples: 3 over 4, 0.383, the square root of 2 minus 10 pi. Real numbers are commutative, associative, and distributive under addition and multiplication. Real numbers obey the inverse property. The additive and multiplicative identity elements of real numbers are 0 and 1, respectively. Imaginary numbers are numbers that involve the square root of negative numbers. In real number math, it's impossible to find the square root of a negative number. To solve this, the symbol I is used, where I represents the square root of -1. This allows the creation of imaginary numbers, which are essential in fields like engineering and complex mathematics. Examples: the square root of -1 equals I, 2i, 3i. The square root of 2, I squared, 3i. An imaginary number, on its own, doesn't represent a number that can be found on the real number line. However, when combined with real numbers, imaginary numbers form complex numbers, which will be explained next. Complex numbers are a combination of real numbers and imaginary numbers. They are written in the form a plus bi, where a is the real part and bi is the imaginary part. Complex numbers are used in various fields, like electrical engineering and quantum physics, where real numbers alone can't describe certain phenomena. Examples: complex numbers hold the associative property of addition and multiplication, the commutative property of addition and multiplication, the distributive property of multiplication over addition. Complex numbers are important because they expand the number system beyond real numbers, allowing for more comprehensive solutions to equations in mathematics. Algebraic numbers. Algebraic numbers are numbers that can be the solution to an algebraic equation. These are equations that involve integers and powers. In simpler terms, an algebraic number is a number that comes from solving an equation, where the coefficients are integers. Example: the square root of 2, because it's a solution to the equation x squared minus 2 equals 0. Algebraic numbers are important in algebra and number theory, as they help define the solutions to many polynomial equations. Transcendental numbers are a subset of irrational numbers. These are numbers that are not the root of any non-zero polynomial equation with integer coefficients. Essentially, they cannot be derived from simple algebraic equations. While all transcendental numbers are irrational, not all irrational numbers are transcendental. Examples: pi, Euler's number. Transcendental numbers play a crucial role in areas like calculus and real analysis, where they often appear in mathematical constants. Quaternions are numbers used to extend complex numbers to 4 dimensions. They consist of 1 real part and 3 imaginary parts. Quaternions are particularly useful in 3D computer graphics, rotations, and physics. They provide a way to represent rotations in 3-dimensional space, which cannot be easily achieved with simple real numbers. Example: 1 plus 2i plus 3j plus 4k. Quaternions are not commonly used in everyday math, but are important in specialized fields like computer graphics and theoretical physics. Octonions. Octonions are an extension of quaternions. They have 8 parts and are used in higher mathematics and theoretical physics. Octonions are part of a more complex algebraic structure known as a non-associative algebra, which means that multiplication does not necessarily follow the normal rules. These numbers are more abstract and have applications in areas like string theory. Example: 1 plus I plus j plus k plus L plus m plus n plus o. Because octonions are used in very specific fields, they are not commonly encountered in most mathematical studies. P-adic numbers are a system of numbers used in number theory. Unlike real numbers, where distance is measured by absolute value, P-adic numbers measure distance based on divisibility by a prime number p. This number system is used for solving equations in ways that are not possible using real numbers. Example: numbers used in solving Diophantine equations, which are equations that seek integer solutions. P-adic numbers have deep connections with algebraic geometry and are crucial in understanding the properties of numbers and equations. Constructible numbers are numbers that can be constructed using only a straight edge and a compass. These numbers come from geometric constructions. Not all numbers can be constructed this way, but many important numbers, such as square roots, are constructible. Example: the square root of 2, as it can be created by drawing certain geometric shapes. Constructible numbers are fundamental in geometry and are tied to ancient problems like the classic trisecting and angle challenge. Computable numbers. Computable numbers are numbers that can be calculated by an algorithm or a computer. These numbers are significant in the theory of computation, which explores what can be calculated and how efficiently it can be done. In other words, computable numbers are those that can be generated or approximated using a finite number of steps. Example: computable numbers are important in the fields of computer science and information theory. Definable numbers. Definable numbers are numbers that can be uniquely described or defined using a finite set of rules or formulas. These numbers might not be easy to compute, but they can be logically described in a mathematical system. Example: certain irrational numbers that are described using formulas or sets like the golden ratio. Definable numbers allow mathematicians to work with abstract concepts that are important in advanced mathematics and logic,